Let's begin. We have a few people here, so we will begin. Hi, everyone. I want to make a few announcements first. For homework 8, Michael and I have received some comments after, like on Friday night, like 1 hour before the homework was due, that oh, it's taking a long time to do all the 900 cases for the diffusion coefficient and the velocity, or my computer can't handle it, etc. And frankly, it's not an excuse, and I tell you why. Because if you can't do it for 900 cases, do it for 10 cases. Do like 3 on k and 3 on velocity, right? You know that the integrators also are inefficient. The implicit integrators are inefficient when the system is not implicit. And as we reduce the diffusion coefficient, that there's less and less stiffness. So, did you try to use the RK45? Or you could do it in chunks. Do first 10, a few cases first, save them, then do a few other cases, or load them up on the CHPC system, right? And just flat out tell us, right, obviously. And it can be done. My computer is 6 years old, and it can handle it, and it did the whole thing, especially with the event trigger. With the event trigger, your simulation, real time, like it will diffuse it within half a second to a second tops. And that would take a computational time. The whole thing took about 7 or 8 minutes. And so, when you're faced with something like this, your grad students and your professors, the people you work with are going to be they're going to rely on your expert opinion, right? And when you say, hey, I couldn't run it on this computer, I just did 5 cases, 10 cases, that's better than nothing, right? So feel free to have that ability to be to be mature in that sense, and say like, oh no, yeah, it didn't work with the 900. My computer was crashing for whatever reason, so I did it for these 10 cases. That's actually a much more useful result, in my opinion, than just saying, oh, it crashed and I'm not gonna submit anything, right? So advice to you in this class, or your other classes, or your career as well, right? Find a way to make it work, right? Find a way to make it work. The next announcement is that I will this will likely be your last homework 8. Although I want you to be familiar with these derivations of Navier-Stokes, what I might assign you this Thursday is my last lecture. I will not be available after that. What I might assign you is tell you, just go and redo the work on the slides, okay? And no deliverable, but I will rely on you to do the work on the slides, to look at the equations, expand them, think about them, because there will be questions on the final about those. There will be definitely questions about those equations, the form, the different terms. So being familiar with all of those is incredibly important. There's no specific assignment I will give. So I haven't made that decision, but 90% you will not have any more homework assignments, but we will do a lot of problems together with Maher, and as after I'm gone. Now, I also posted the videos from previous years of all the problems that you will be solving with Maher. So Maher will record, will do the lectures, and I think he will be in person. He will let you know, and he will do the lectures. He will explain the problems, solve them with you. And he will record those lectures as well. We will post them, but there will also be the lectures I did from when I taught fluid mechanics. They're already posted on the front page. So all of those problems, you will have 2 to 3 problems like that on your final exam. Third or fourth announcement, whatever. The third announcement is that the final exam, you'll see 2 pieces on Canvas. One containing about 20 to 25 low stakes questions like, is this true? Select which applies, compute this, really quick low stakes questions, like maybe about a minute each or 30 seconds each. That's the online version on Canvas. You fill that out, you're done with that. Then you take the second, there's another exam called the handwritten exam. okay, where you will be given, you'll just work on the sheets that you will be given. So Michael will distribute sheets to you, and you'll work with answer sheets and everything, and you'll get equation sheets as well, and you will work through those. So that will be your second part. Those who are taking the exam remotely for whatever reason have already coordinated with me. They will, so for you, if you're in class in person, you don't have to do anything on that second part of the exam. It's just there as a placeholder for me to put a grade on it. But those taking it online remotely, they will have to take pictures of their solution and upload them. Okay. But either way, you will be given the sheets. You'll take the online version of the exam, and then the rest you'll do it by hand and then give it back to Michael. Now, needless to say, it's very important you redo the problems we're doing in class. There will be about 5 to 6 examples covering all sorts of possible combinations. And as you will see when we solve these Navier-Stokes, as I will explain, or Maher will explain, whoever gets there first, we're just trying to convert these equations into either a Couette or a Poiseuille flow problem or a combination. And you'll understand what that means. And all of those are going to be just have a diffusion term, because it's linear, equal to 0 or equal to either gravity or a pressure gradient or both. Okay? And that's it. So you'll either get a parabolic type profile or a linear profile. And so, but we can manipulate the problems and the problem setup in different ways to make you think about kind of how to approach it. But your goal is to always reduce it to a diffusion equation, as we will explain later. Okay, so this will become clear once we hit that stage. Now, when I come back to what we were doing here, we were looking at tensors, and specifically where we left off last time was the advection tensor. We talked about rank 2 tensors, etc. Talked about dyadics, and last we left off was talking about the divergence of that advection tensor. If you have questions, let me know right now. Questions about what's happening and what's going to happen in the coming days or weeks. If not, just if you think about something later, just email me, send me a message on Canvas, and we'll make sure you copy Michael as well, and then we'll answer you. Okay, so going back to the advection tensor, we wrote this in this dyadic form, which many of you, this might be the first time you've seen this. And remember, the dyadic is simply trying to track, in our nomenclature, it's trying to track two things: a momentum component and the direction in which that momentum component is advecting. So, and I gave you this example when we left off. For example, W rho V, we know from our convention is that this is the Y momentum component, rho V, being advected in the Z direction with the W velocity, okay? So the dyadic form enforces that idea by adding this, by tagging along this Kj unit vectors. So this Kj unit vector is a dyadic, okay? It tells you two things. It tells you that the last index tells you which component is being advected. Indeed, J corresponds to the Y momentum component, which is rho V. The first unit vector in that dyadic tells you in which direction we are advecting the J component of momentum. And in this case, it's in the K direction. So you see the W over here. So we're consistent. So our words, our convention for W rho V or U rho U or W rho U or U rho W is consistent with this dyadic nomenclature. It enforces it. It enforces that nomenclature. Now, next, what we're interested in and what makes it to the momentum equations, if you remember, is the divergence of that advective flux. Why? Because the divergence tells you this is the net that's being left in the control volume. So the advective flux itself is just what's coming in and what's leaving. The divergence of the advective flux is the net of what's coming in and what's leaving. So you subtract and add whatever is leaving, whatever is coming in. So whatever is left in your control volume, that's the divergence of the advective flux. And we talked last time that you asked, what does the divergence of a tensor return? And we argued that the divergence of a vector returns a scalar, but the tensor is like one rank higher than a vector. So if the divergence is consuming a rank, one rank, it must take, for a rank 2 entity, which is a tensor of rank 2, the divergence is going to convert it into a rank 1 tensor, which is a vector. And indeed, we should expect that the divergence of a tensor returns a vector. Now, if you remember, this is from the previous equations, and to confirm this idea, if you remember from the previous equations, when we added I, j, k to the momentum, to each momentum equation, to x momentum, y momentum, we ended up with this, with these three individual contributions. Div u rho u for the x momentum contribution, div u rho v for the y momentum contribution, div u rho w for the z momentum contribution, but we added I, j, k to those because that's enforcing that this is x momentum, because x momentum is in the I direction, y momentum is in the j direction, and z momentum is in the k direction. Now, these here, each entry here is a scalar, right? Because u rho u is a vector, u rho v is a vector, its divergence is a scalar. So these eventually make it as scalars into their individual momentum equations, all right? So now this leads us to this definition. The divergence of the advective flux tensor returns a vector. This is this vector. The components of this vector correspond to the x, y, and z momentum net advective flux contributions respectively. So the divergence of the advective flux tensor is a vector. The first component, the first entry in that vector is going to be this guy here, right? And that makes it into the x momentum equation. The second entry in that vector is this guy, and that makes it into the y momentum equation. This is the net advective flux of the y momentum component. And finally, this is the net advective flux of the z momentum, and this makes it into the z momentum equation. Now, this is enforced by the idea that this has a k, this means it goes into z momentum, this has a j, goes into y momentum, this has an I, goes into x momentum, okay? All right, so now my next step is I want to use, how can I compute this? I know this is true. I know I want the left-hand side to be equal to the right-hand side because the right-hand side was derived one equation at a time. So if I were to learn how to do a divergence of a tensor, it needs to give me this answer, agreed? So I need to build my way of computing the divergence of the tensor. So far, right now, we don't know how to do this. We don't know how to do this. But we know it must be equal to this. Agreed? Okay, so next I want to teach you a way of how to compute this using dyadics and then using tensor notation. We will learn to do it in two ways. The first way is using dyadics, and that's to me is the most straightforward because all you have to do is simply do a dot product the usual way we do divergences. Okay, so I'm going to take my nabla operator, d by dx in the I direction plus d by dy in the j direction plus d by dz in the k direction, and simply dot it with my dyadic form of the advection tensor. Okay, is this legal? Absolutely. Is this allowed? Absolutely. Okay, all I'm doing is taking a dot product between a vector operator and a tensor. Okay, now this is very clean and clear compared to other ways of doing this, where I told you last time, some people represent this as a matrix. And then they do a vector matrix product with nabla, and they put nabla as a column or row vector, and it messes everything up. Okay, this is clear here. All I'm going to do is simply algebra. Because now with the dot product, I can distribute each term with all the other terms. So I'm going to take this d by dxi, and I'm going to dot it with each term over here and see what happens, okay? So then the result is simply I'm dotting unit vectors. So let's see how we would do this. I'm going to take a few terms and then you can figure out the rest, okay? So the first term, I'm going to take d by dxi, and I'm going to dot it with the first entry in my advection tensor. Now you can tell this is this is going to be I dot ii. So I dot I is 1, and you're left simply with I, right? So I dot d by dx of all of this guy, and that gives me I dot ii because I unit vector doesn't change with respect to x. U rho u remains under the x derivative, and then the result is this component d by dx of u rho u with the I unit vector. Now I'm going to take this and dot it with the second component here. So d by dx I dotted with u rho v I j. And again, I'm simply taking I dot d by dx u rho v I j. And ij are constant, they don't change with x, so they can be pulled out of the derivatives. And then I dot I is 1, and you're left with j, okay? And then same thing, you dot this with ik, and then you can see the trend here. I dot I is going to return 1, so this is going to give you d by dx of u rho w k. Now, you take this and dot it with v rho u j I. What is that going to be? 0, because I dot j is 0. Agreed? So if you do this, and then you get I dot j I. Now I dot j is 0, so it's going to be 0. Okay? And then you continue. You continue this procedure and you collect the terms together. What you're going to get is this, exactly what we had on the right-hand side. This works just magically, just doing algebra. You're dotting, you're distributing the I, j, and k vectors and the derivatives across all the terms. And this gives you the x momentum contribution, which is div u rho u over here. And the y momentum contribution is div u rho v. And the z momentum contribution is div u rho w. Now, you need to do this by hand. So when I tell you, I'm not assigning you a homework on Thursday, but go redo the work we did in the slides. You got to go and do this by hand. Okay? And as you're doing it by hand, you're going to get stuck. So you ask questions. You have 3 or 4 weeks before the final exam. Okay? Because I guarantee you will be asked about this. I guarantee you're going to be asked about this. Okay, I'm going to give you a dot product of two things, right? A tensor and a nabla operator or a vector, and in dyadic form tell you figure this out. Which one of the following is true? Okay, so you need to be able to do that distributive operation. It's really simple, guys. Just simply dotting. Just the same way you dotted two vectors, now you're dotting a vector with a tensor. And if the tensor is in dyadic form, it becomes really straightforward. Okay? You're just distributing the dot product. Now, another way to express a tensor is index notation. Now, again, is this going to be a big deal for your life? I don't know. My job is to make sure that you've seen this, you know where you come back to learn more about it. If you end up in modeling, you're going to be using this a lot. If you don't, yeah, it might be something you've seen, but it's something you need to see as a chemical engineer, okay? And this is, I'm barely scratching the surface on this, just giving you enough to make you be able to talk about this. For a rank 2 tensor, remember, a rank 2 tensor, at least for the advection tensor, we had momentum component and direction. So we had two things to track. And therefore, we need two indices, just the same way with tau ji. We need two counters, two indices, to describe the advection tensor. Okay? So in general, for any rank 2 tensor, there are two things you're tracking. There's a component and direction, or there's a direction and component, whatever your convention is. So there's two things you need to track. So you need two counters, two indices. So in this case, we're going to write our momentum advection tensor as uj rho ui. Now this will be consistent with my convention on tau ji. The second index corresponds to the momentum component, and the first index corresponds to the direction. So when we talked about tau ji, we said it's the diffusive flux of the I momentum component and the j direction. uj rho ui is the advection of the I momentum component in the j direction. Okay? And this is again consistent with our nomenclature that we've been using. V rho w is the advection of the z momentum component in the v direction, right, on the j direction. This is consistent with all of that. So if you use words and you repeat it over and over again, this becomes stuck in your mind, okay? Now here I reinforce the idea that this is I and j can assume only any value between 1 and 3. And remember, 1 corresponds to the x, things in X, 2 corresponds to things in Y, 3 corresponds to things in Z. Now, in our nomenclature, the first index denoted by J here corresponds to the direction in which the advective flux is moving information, and the second index, I, is the component that is being advected, okay? Now, for example, U1 rho U3 is what? This is the advection of the third momentum component being advected by the first velocity. In other words, this is the advection of Z momentum, which is the third direction, in the X direction, in the third component of momentum, which is in the Z direction. That's its advection in the X direction, okay? In the X direction by U1. U2 rho U1 is the advection of X momentum in the Y direction, okay? That's equivalent to V rho U, okay? So all of those combinations, you have 9 total combinations because there's 2 indices and each index has 3 entries. So you have 3 by 3, you have a total of 9 components in all of this. Okay. Now, tensor notation makes computing the divergences very, 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 very easy. But I need to teach you a few things to be able to do that. So if you don't like the dyadic form or you have a philosophical issue with that, I had a student who had a philosophical issue with it. He refused to use it. I'm like, okay, just use the tensor index notation. I don't care, okay? As long as you get the correct answer in the end. Okay, the divergence of the advection tensor is given by this index notation, and I'm going to spend some time explaining this. It's the partial derivative of uj rho ui, which we just learned, okay? Uj rho ui is the advection of the I component of momentum in the J direction, but differentiated with respect to xj. Okay, be careful here. This J is the same index as this guy, because you might see this partial uk rho ul by partial xk. Doesn't matter. An index is just a symbol, okay? But you have to be careful that this index here at the bottom corresponds to the direction index on your tensor. This is very, very important. Okay. Now, how on earth would this reproduce my 3 contributions, which each contains 3 terms summed together? Okay, so we need to build on this a little bit. Okay, a repeated index in a tensor notation, when you see an index repeated, this immediately implies summation. So here, the J index is repeated, so I know this is going to imply a summation. What does this mean? Let's give some examples. So for example, if you see AI, BI, and I tell you this is a tensor notation, then this automatically implies that you're summing over I here. A1, B1 plus A2, B2 plus A3, B3. Why? It's a convention. It's a convention. Instead of having to write summation of AI, BI, you just write AI, BI and say we are using the summation convention. DUI by DXI, because I is an index that's repeated, that also implies summation. What this implies is this is DU1 by DX1 plus DU2 by DX2 plus DU3 by DX3. Okay? Very simple. What if you see DUJ by DXJ? I don't care. J is a dummy index. But I see it repeated. So I see UJ, XJ in the same term. Then I need to sum up. That's DU1 by DX1 plus DU2 by DX2 plus DU3 by DX3. So I do anticipate that this is going to turn into a summation. Okay? But bear with me. This convention is called the Einstein summation convention. So when Einstein was building his general theory of relativity, he needed to use these rank 2 tensors, okay? The gravitational tensor and the curvature tensor G mu V and T mu V, whatever symbols he used. So he related the gravitational tensor to the curvature of space tensor G and T, and he used mu and V as his subscripts. But in the process of the derivation, he had many derivatives and repeated and tensors that required to do summation. And to avoid having to write a lot of summations, he said, I'm going to assume that whenever I have a repeated index, this implies a summation. So whenever you see AIBI, This means A1B1 plus A2B2 plus A3B3, okay? Now, the summation convention has some rules. It says that when an index variable appears twice in a single term, okay, in a single term, and is not otherwise defined by saying, oh, this only takes the value of 3, or if it takes the value of 2, so it's not an array value or something like that, it's just a vector, an entry in a vector, then it implies summation of that term over all the values of the index. Okay, so I'll give some examples. AI plus BI is not a repeated summation because I is not repeated in the same term. Okay, so be careful about that. Now, if you had AI BI plus CJ DJ, in each term there's a repeated index. So AI BI, that implies A1B1 plus A2B2 plus A3B3, and CJ DJ, there's a repeated index there. So that also implies C1D1 plus C2D2 plus C3D3. Now you can use also the same index, AIBI plus CIDI. That also gives you that same summation, okay? So the only exception you need to be careful of is this guy. When you are summing over when you have a single term that doesn't have a repeated index, then you have to be careful about that, okay? Otherwise, it's always repeated indices. Okay, so how would this help us? We're going to come back to this term. Now, in this term, I have a repeated index, j, right? So I have duj and dxj. So I know I'm going to sum up over uj and xj. But I have another index here that's not repeated. What do I do with this index? Well, I only sum over the repeated index and keep the other index free. Okay? Now, another way of saying this is that I'm going to have three versions of this for each value of I. Remember, I goes from 1 to 3. So for I equal 1, I'm going to have a repeated summation. For I equal 2, I'm going to have a repeated summation over j. And for I equal 3, I'm also going to have a repeated summation over j. So here's an example. Suppose I have aj, bj, ci. This is going to result in 3 different summations. The first summation when I equal 1, so I'm going to fix I. And then the second summation when I equal 2, third summation when I equal 3. So when I equal 1, I'm going to fix I. That's going to be C1. But I still have AJ, BJ. And because it's repeated, J is not fixed. It's going to sum up over all J. This will be A1, B1, C1 plus A2, B2, C1 plus A3, B3, C1. Okay? When I equal 2, I'm fixing I. But J is not fixed because it's repeated. We're going to sum over J. It will be A1, B1, C2 plus A2, B2, C2 plus A3, B3, C2, and so on. When I equal 3, again, I'm going to fix I, but J is repeated, so J is going to be defined by the summation, right? So I'm trying to tie this guy, okay? This is identical to this. Here I have J that's repeated, but I is my free index. So I define what I is when X momentum, I equal 1. When dealing with Y momentum, I equal 2. When dealing with Z momentum, I equal 3. But in each case, I'm summing up over J. Okay? So let's see how this works. So duj rho ui by dxj, I'm going to have 3 contributions, right? Because I have 3 momentum equations. There's 1 entry for X mom, 1 entry for Y mom, 1 entry for Z mom. Okay, so I have these listed here. For I equal 1, that's my X momentum contribution. Then I fix I, so this becomes duj by duj rho u1 dxj, and then I sum up over j. That becomes du1 rho u1 by dx1 plus du2 rho u1 by dx2 plus du3. You just go over the summation. Now, this is the X momentum contribution, right? If you remember, this is the X momentum contribution. du rho u by dx plus dv rho u by dy plus dw rho u by dz. That's why it's so important. I tell you, put the advecting velocity before the advected information. I know you can rearrange this. Oh, this is d rho u1 squared. You're not being smart by doing that. You're only confusing yourself. Keep it in this form. It's clear and clean and connects with all the index conventions that we are using together. See this beautiful symmetry here. Same thing when I equal 2. For I equal 2, I'm advecting the y component of momentum. Okay, so the contribution is going to go in the y momentum equation, and I'm gonna sum up over j. This becomes du1 rho u2 dx1 and so on. You're fixing rho u2. Again, if you remember, this is the contribution of the advective flux to the y momentum equation. It's du rho v by dx plus dv rho v by dy plus dw rho v by dz. Okay? Look, I can pontificate and talk about this all day long, but until you go and do it by hand, you are never going to learn this. Because the minute you start writing it, you're going to be like, huh? What is being fixed? What am I rotating? You come back to the slides, you come back to what I'm talking about, but you have to do it by hand. I cannot learn it for you. I already know how to do it because I repeated it hundreds of times. Okay? But it's not rocket science. It's just new knowledge that you're learning, and I'm giving you the rules on how to do it. Same thing for the z momentum contribution, and I equal 3 in this case, repeated summation on the repeated index, and you're good to go. Now, this should hopefully explain to you why I put I didn't write this as ui rho uj, okay, because eventually I'm going to be transporting the I momentum component. So my time dependent term is going to be d rho ui by dt. And so I need to make sure all the terms that are being transported have I, which I'm choosing. I say I equal 1, I equal 2, I equal 3. And if there's a repeated index, it's going to be on another index, j, k, or whatever. Okay, so there will be no repeated indices on I because I is going to be predetermined. Okay, I'm going to choose what I is. I'm going to say I equal 1, do everything else. I equal 2, give me everything else. Okay. Next, we move to the stress tensor. Now that we've gone through the works, the stress tensor discussion becomes easier because the stress tensor is also a tensor. It's a rank 2 tensor. It has 2 indices. We can already discuss that. Tau ji is the diffusive flux of the I component momentum in the j direction. Okay, so tau yz is the diffusion of the z momentum component in the y direction. It's the diffusive flux. Okay. Now we used index notation here. I'm going to remind you of this, but the same way that we expressed the advection tensor using dyadics, we can also express the stress or diffusion tensor in dyadic form. And it looks like this. Tau xxii, so that's the diffusion of the I component of momentum in the x direction. And this is consistent with my nomenclature, I the second I corresponds to the second index, and the subscript, and the first I corresponds to the first index. Tau yx is the diffusion of x momentum in the y direction, and the ji over here, it confirms that. It's the same way we did about advection, right? The second index corresponds to the component of momentum that is being diffused. The first index tells us which direction it's diffusing in, okay? And when you write it this way, it's completely legit. It's not ambiguous. It's clear. You don't need to put it in matrix form. Eventually, for the fluids we will be dealing with, it will be symmetric. What that means is tau yx and tau xy are going to be equal. So there's less risk of screwing things up. But when you're not dealing with symmetric tensors, you will get in trouble if you don't use this nomenclature. Okay? So now I'm interested in the net diffusive flux. And the same way as we did for the net advective flux, we have to take a divergence to get the net diffusive flux. Now we know the answer. Again, if we don't know how to compute div tau, which we should know by now, but suppose we didn't know how to compute div tau, we know what the answer should be, right? Because we derived this individually for x momentum, for y momentum, for z momentum. This was the net diffusive flux for x momentum, and this was the net diffusive flux for y momentum, net diffusive flux for z momentum, okay? And you see how the second index here is fixed into x, because that's the x momentum that's being diffused. The other indices tell us what the contribution is in the different directions, okay? Okay, good. Use words. I really urgently, strongly urge you to use words as you talk about tau yx and tau xy. Say, okay, tau yx d by dx, tau yx. What is tau yx? Diffusion of x momentum in the y direction. All right. So by analogy with the divergence of the advective flux, we can also do the dot product operation by dotting the nabla operator with the dyadic form of the stress tensor. And it should also return a vector. Now, it should return this vector. The components of this vector correspond to the x, y, and z contributions of the net diffusive flux in the for x, y, and z momentum. So here's the formal definition. The divergence of the stress tensor returns a vector whose component, not who components, whose components, okay, whose components correspond to the x, y, z momentum net diffusive flux contributions respectively. So diff tau returns a vector. The first entry of that vector is the net diffusive flux in x momentum. The second entry is the net diffusive flux in y momentum. And the third entry is the net diffusive flux for z momentum. Okay? Now, you can also use dyadics to compute this. So the same way we did with the advective flux tensor, you just simply distribute this, okay, to these guys. And I dot I is going to give you I dot J is going to give you 0, and I dot K is going to give you 0, I dot I is going to give you 1, and so on and so forth. So you continue doing this through the entire procedure, and lo and behold, what you will get the correct answer. Okay, you will get the correct answer. So we know this way that this operation is true and correct when done in this order. Okay, the other way of doing this is also using tensor notation. Okay, and the same way we did with the advective flux tensor uj rho ui, the divergence of the diffusion tensor looks the same. You're differentiating with respect to the direction index. And notice here, be very careful. This J corresponds to the direction index, to the first index in our convention. If people are flipping the meaning, if they're using tau ij, J means component and I means direction, then this should be d tau ij by dxi. Okay, but then they're choosing what J is. So whatever index notation you choose, be smart about it. What are you diffusing? Which index corresponds to what component you're diffusing? That's the one you're choosing. You say, I want the x momentum, y momentum, z momentum. You choose that. In this case, I'm choosing what I is, but J is gonna be a repeated index summation. Okay? Remember, you hold the index corresponding to the momentum component fixed. So you are choosing. So when I say, what is the contribution to the x momentum equation? Then you fix I, because we chose I to be the momentum component, and then you repeat the summation over J. Okay? Whatever indices you choose, make sure you understand what is being differentiated with respect to what. A repeated index is going to mean you're summing over that. The other index is going to indicate which component of momentum you are dealing with. So similarly here for I equal 1, that's x component of momentum. The net diffusive flux that is going to make it to the x momentum equation is going to be d tau j1 by dxj, because I fixed this is only the contribution to the x momentum component, and you're going to get these guys. And now remember, this is tau xx, tau yx, tau zx, right? So this would be d tau xx by dx plus d tau yx by dy plus d tau zx by dz. Okay, and same thing for the other guys. Repeated index, repeated index. Again, look, should you leave this lecture remembering this? No. But you have to do it. You have to do it by hand. If you do it about 3 to 5 times, it will stick. Okay? And you have to do it. Now, I need to warn you again. index notation. You might see people index things as tau ij, tau ji, tau kl. There's a whole lot of different index. These indices are just dummy, okay? But as long as you know what index is being repeated, then the remaining index is going to indicate which component of momentum this is gonna belong to, okay? That's it, very simple. Now, once you're done with all of this, we're gonna go back to these Cauchy momentum equations. We have three forms of these equations. The vector dyadic form, okay, which is this guy. That's kind of nice and compact, but here you have to use dyadics to explain this. Or the tensor form. Now this becomes clear here. Why did I choose I as the component of momentum I'm moving? Because I want my, whatever I'm advecting, whatever I'm transporting, to have an I index. I chose that. So because the time derivative term contains rho ui, I'm fixing that. I'm saying, okay, what is the x component of momentum, the x momentum equation? Then that tells you, oh, here I'm going to have rho u1. What is the y momentum component? Here I'm going to have rho u2. And then that should propagate through the rest of the equations, right? You say I equal 1. What is this equation when I equal 1? Oh, it's going to be this guy. What is this equation when I equal 2? It's going to be this guy, and so on, okay? So you have these three forms of the equations. In your homework, in your exams, I will give you an equation sheet, right? Putting these equations. The equation sheet is already in Canvas, so you should check it out under supplementary material. There's like 7 pages in it. Okay, we will print it and give it to you as well. You're welcome to save it, print it for your own use. But we will give you the expansion of these terms, or every possible combination of these equations in Cartesian, in cylindrical, and in spherical coordinates as well. Okay, they all look similar. Okay, but these are the equations. Now, these are the Cauchy momentum equations. They describe the motion of a continuum, whether fluid or solid. When you have a solid, you're not going to have advection, so you knock out the advection term. You're not going to have pressure or gravity term, right? Or you might have some advection if you have a very kind of mushy solid, right? Or a non-Newtonian fluid, etc., right? So, but these are very general, okay? These are one layer above the Navier-Stokes equations, which are only for fluid flows, okay? So the next step now is to just make sure the units are consistent. And if you look, you only need to look at the first term to double check what your units are. And I'm claiming this is momentum per unit volume. Indeed, this is rho u over time. So mass per unit volume times length over time. And you combine these and you get Newton per unit volume, Newton per cubic meter. And indeed, these equations transport momentum per unit volume. Okay? They transport momentum per unit volume. And you can double check each one of those terms to make sure there's dimensional consistency. Okay. Now, these are the Cauchy momentum equations. And with the mass conservation equation and energy equation, let's say, so I want to count how many equations we have and how many unknowns we have. So if we count mass conservation, that's one equation. Momentum, we have 3 equations, right? U, V, and W. Agreed? And I have one energy equation and probably one equation of state. So I have 6 equations. Okay, but how many unknowns do I have? I have rho, density, U, V, W for the velocities, right? I have pressure, 5. I have temperature or energy, 6. And then what else do I have? I have 9 components of the stress tensor, which we didn't define. They're only called tau xx, tau yx. We don't know what they are. They're just new variables, right? There's 9 of them. So 9 plus 6 is what? So we have a total of, hold on, did I count this wrong? So 9 plus 6 is 15 unknowns. 15 unknowns, okay? So we have 6 equations, 3 momentum, 1 mass, 1 energy, 1 equation, and 15 unknowns, okay? So you need to list the unknowns, rho, u, v, w, p, and t. So I didn't include T over here. That's my mistake. That's why I put 14. Rho VW T and 9 components of the stress tensor, right? And the system is not closed, okay? The trouble is coming from the stress tensor because it added, if we were only dealing with rho, U, V, W, P, and T, we would have 6 unknowns and 6 equations. Agreed? But the additional 9 components of the stress tensor made this an unclosed system. Now, in general, we call this, in transport, in fluid mechanics, solid mechanics, we call this a closure problem. You have more unknowns than you have equations, okay? And the only way around this is to connect the unknowns to the known quantities or develop new equations for the unknowns, okay? We are gonna take the former path when we're dealing with fluid mechanics. Because that's the only way, that's the easiest way forward. That's the only way that this can be done. Now, this is a general closure problem. The specifics for fluid mechanics, the closure problem is that we don't know what the stress tensor is unless we define what the fluid is. So this is going to take us into a detour to figure out now what can we do with the stress tensor. Remember, the stress tensor was also called a diffusion tensor. And if you remember our diffusion mechanism, it was simply based on gradients, right? So we should be able somehow to connect the diffusion or the stress tensor to some gradient, very likely the velocity, because it's not the pressure or the density that are causing the diffusion between these elements. It's the velocity, the motion of the fluid elements as they're deforming. Okay, so we should be able, hopefully, to connect the stress or diffusion tensor to the velocity field. And if we do that, we have a closed system. Okay, so we're going to take a little detour now and start focusing on the stress tensor. Turns out that we can relate the stress tensor to the velocity field. But this is a function, this is dependent on the type of fluid you are working with. Now, this is going to take us a little bit into solid mechanics and continuum mechanics, which is beyond what I want to cover, but I'm just going to give you enough flavor, okay, to connect and relate to this. So in solid mechanics, we have 2 primary concepts called stress and strain. Who's heard of strain? Strain is simply a rate of displacement. How fast are the particles moving? So if you take a piece of, where are my glasses? The best experimental tool. So when I'm deforming this, right? See how it deforms? I'm putting force, and the force is causing deformation. So there's a direct relation between force and deformation. And more specifically, there's a relation between force per unit area, which is more universal than just force, okay? You say, oh, like if I apply 10 newtons, it's gonna deform by 3 centimeters. That's meaningless. What is more important is if you apply 10 newtons per square meter, what's the rate of displacement? Do you get 3 centimeters per second or 1 millimeter per second, right? So that is the more universal way. So that's how they do it in solid mechanics and continuum mechanics. You take a stress, which is force per unit area, and you relate it to deformation per unit time. Force per unit area is called stress. Strain is deformation, strain rate is deformation per unit time. And we can relate the stress to the strain rate, okay? And now strain and deformation occurs in all sorts of directions. So you can deform this way, you can shear. So there are actually 9 directions of strain, just like this, just the same way there are 9 directions, 9 components of stress. And in general, we describe this as a stress-strain plot. Okay, so here what I have on the y-axis, I have stress, and on the x-axis, I have strain rate or rate of displacement. I'm going to start with this blue curve, okay? This blue line here, which is called Newtonian fluid. Now, this is specifically looking at shear stress. If you are shearing the material or the fluid, how does it deform? You're not compressing it, you're shearing it like this. What this is saying is that for Newtonian fluid, this blue curve, it's telling us that there's a direct linear relation between stress and strain. If you double the stress, you're probably going to double the strain, or you're going to change it by a constant amount. Okay, you're going to deform by a constant amount. This defines what we call a Newtonian fluid. Water is a Newtonian fluid, for example. Air is a Newtonian fluid. But that's not the only kind of fluid. There are all sorts of other fluids that behave in the weirdest ways. The other one is this one in green called dilatant fluid or shear thickening. What you notice here is this initially, for very little stress, think of stress as force. I'm applying force. For very little stress, over here in this region, there's a lot of deformation, right? There's a lot of deformation on the x-axis, a lot of deformation. But suddenly there's a point where the stress is so high, then the fluid becomes resistant to displacement. So initially it's kind of easy displaced, and then it suddenly becomes hard to displace. Okay, it thickens. So that's why we call it shear thickening. The more shear you apply on the fluid, the harder it becomes. Can you think of a fluid that does that? Like a really fancy, cool experiment that people have shown and that's taken the internet by storm. Okay, let me give you this example. Let me show you the movie. Have you seen this movie? Okay, what is happening here? This is what cornstarch, guys. Cornstarch with water, okay? When they're running on it, you're applying a strong force, okay? So you are, whoops, let me go back. When you're jumping hard and running on it, you're applying high stress. So the fluid is gonna thicken, it's gonna harden. It literally can behave like a rock. So if you take a hammer on this and hammer it so hard, it will bounce the hammer back. But see the kid who fell and sank? Once he fell, he didn't apply force anymore. He was like kind of barely pushing on it. He started sinking. Why? Because he was in this regime and the fluid started deforming around his body and he started sinking. So cornstarch in water, you can try this at home. You can find how much combination you want to put with cornstarch and water, put it in a bowl, and like take a hammer at it. If you sit the hammer on it, it will sink very slowly. But then if you hammer it, it's probably gonna break the vase or the bowl that you're putting this on. Okay, so that's called a shear thickening fluid. The more stress, the more force you apply on the fluid, the harder, the more resistant it becomes to displacement. And look, it kind of goes up exponentially. On the opposite side of that, on the Newtonian curve, you have shear thinning fluids. What does that mean? It's the opposite of shear thickening. It means at low shear, at low force, you're going to have resistance to motion. But at high force, it's going to thin out and it's going to become very, very easy to displace. Common examples are your toothpaste. You grab your toothpaste, you hang it like this. It's not going to flow out. You have to apply enough shear for it to start moving. Okay? Paint. Why do you apply the roller? Paint is a shear thinning fluid. On its own, it's not going to displace or deform unless you start putting more force on it, so you're going to be able to spread it. Okay? This is also called pseudoplastic fluid. And then there are other fluids, like an ideal plastic fluid. There is no displacement at all until you breach a minimum stress. And then it's going to start displacing like a Newtonian fluid. Okay? And then you have plastic fluids, which are kind of higher curve than these shear thinning fluids, okay? Now, what we deal with commonly as chemical engineers, you will mostly deal with Newtonian fluids, but you will also deal polymer solutions are typically pseudoplastics, or full plastic fluids. So you might be dealing with these non-Newtonian fluids as well. Which equation do you use in that case? You need to know what this stress-strain relation looks like. So it will be given to you normally. Okay, and then you go back to the Cauchy equations, you substitute the stress tensor, and you figure out what the equations are. But for Newtonian fluids, we know what the stress-strain relation is, and strain, which is strain rate, which is deformation rate, which is essentially related to velocity, directly to velocity, because velocity is the displacement of fluid elements, fluid particles, right? So you can tie that strain rate to the velocity field. And, you know, you don't have to worry how this is derived from a lot of experiments and theory, but this is the Newtonian stress tensor. It's, at first sight, it looks very complicated, but it's really not. It's simply two derivatives of the velocity multiplied by some constant or a coefficient, which could depend on other things. This we're going to call viscosity, plus some other terms. So let's describe these terms. This first term is the coefficient viscosity. So that's the proportionality between the stress and the strain rate. Viscosity, we said, is a measure of how much, it's the slope. Okay, so viscosity is the slope on that Newtonian, on the Newtonian line. Okay, viscosity is that slope. It's the proportionality constant, if you will, between the stress and the strain. In general, it is dependent on temperature. It can also depend on space, okay? Because you might have different fluids, right? Now, what is this symbol here, delta Ij? It's just a convenient symbol. It's called the Kronecker delta. So Kronecker is this physicist who needed to define this thing. It's very simple. Delta is 0 when I is different than J, and it's equal to 1 when I is equal to J. So for tau 11, tau 22, and tau 33, delta is 1. For all the other components, it's 0. Okay? Now this delta is going to multiply another coefficient called lambda and this div u. Now remember div u, we said if div u is 0, the flow is incompressible. But when div u is not 0, there's a contribution of this div u to the stress tensor. Okay? So it's not always 0. Lambda is called the second coefficient of viscosity, and in general is taken as minus 2 over 3 mu. Okay? So in the most general case, when you're dealing with air or gas dynamics or compressible flows, all of these terms need to be there. Now, this looks like a mystery. It's not a mystery. You simply put J and I here and figure out what these are. And I'm going to do that here for you. Tau xx, that's tau y1. Okay? Tau y1, you have du by dx plus du by dx because I and j are 1. And delta 11 is 1. Lambda is minus 2 over 3 mu and div u. So that gives you tau xx. Okay? Tau yx, well, in this case, j is equal to 2 and I is equal to 1. And you get du by dy plus dv by dx. Delta 2,1 or delta 2,1 is equal to 0. So this term doesn't exist. And same thing here for tau zx. This is going to be delta 3,1, and you substitute 1 and 3 and you get the derivatives. There's no repeated indices over here whatsoever, and you can build all of these stress components. Now, for a Newtonian fluid, the stress tensor is symmetric. Tau yx is equal to tau xy, tau zx is equal to tau xz, and tau zy is equal to tau yz. You see how I put the blocks in color over here? And then the terms on tau xx, tau yy, and tau zz, they look however they want to look like, okay? Now that you have this, you can take this and plug these in the Cauchy equations. So if you remember all the way back in the Cauchy momentum equations, we had here tau xx, tau yx, tau zx. You simply take those terms and plug them back in here, okay? And then you'll get the equations for Newtonian fluid. In your equation sheet, you're going to see the Cauchy equations, and you're going to see the general when we substitute tau xx, tau yx into these equations. You see both versions, okay? So they've done the substitution for you. But if you're smart, you should go and do the substitution yourself and compare that you get the same answer, okay? All right, so let me come back here for the stress tensor. So now that this gives us closure, because finally my stress tensor is a function of my other unknowns, u, v, and w, right? So now I have only 6 unknowns and 6 equations. Conservation of mass gives me 1 equation, momentum gives me 3 equations, energy equation gives me 1 equation, and equation of state gives me the 6th equation. I have 6 equations in total, and I have 6 unknowns, rho, u, v, w, p, and t. 6 unknowns, 6 equations. The system is closed. And these equations in this form, they are called the general equations of gas dynamics. They work for compressible, incompressible fluids. They work for turbulent, non-turbulent flows. Inside of them, they contain all the physics that you need to solve any fluid flow problem. Now, when the flow is incompressible, certain things simplify, okay? And the equations get reduced, but still they are derived from this general set of equations. So gas dynamics sits right under Cauchy equations. Cauchy equations are in terms of a stress tensor. Once you specify the stress tensor, if you choose a Newtonian fluid, you get the equations of gas dynamics, okay? They're not Navier-Stokes, they're just equations of motion for gas dynamics. Navier-Stokes is only a special case when the flow is incompressible, okay? Now, if you specify a different stress tensor, they're not gas dynamics. They're a polymer flow equation, okay? But they're all derived from that Cauchy set of equations, okay? You might not need an energy equation, then you ditch that, okay? If you're doing with polymers, isothermal, ditch the energy equation, you don't need that. Okay. Now we have a bunch of simplifications that we can do. We're not going to go over any of those because this is not a fluids course, but you've probably heard of them. There's irrotational flow, there's inviscid flow, there's incompressible, there's boundary layer equations, Bernoulli's equation, Euler's equation, etc. All of those are special cases of the general equations of gas dynamics. They're not different equations, they're a special case of that, okay? They're just simply a special case of these equations. These are the most general equation set. The one we will talk about today is incompressible constant density flows, okay? Because that will give us the Navier-Stokes equations, all right? So when we go to Navier-Stokes, we know that the density is constant, okay? So that is going to tell us a lot about the flow. It's going to simplify things quite a bit. And we're going to do this together. We will start with mass conservation. If you take the equation of mass conservation, we know rho is constant. And so technically the time derivative is 0. And also that term, I can pull out the density out of it, okay? So more specifically, I can write this term, this div rho u, as rho div u plus u dot grad rho. Now when the density is constant, this term is 0 and this term is 0. So you are left with div u equal to 0. So the continuity equation simplifies to the condition that your divergence of velocity, also called dilatation, is equal to 0. Was there a question? Okay, let's continue. Now, in tensor notation, I want to write this in index notation. Div u is also written as dui by dxi. Repeated index, that's du by dx plus dv by dy plus dw by dz equal to 0. Remember that because I'm going to use it in the next slides, okay? So that's the index notation for the conservation of mass of incompressible flow. Okay, next, so let's clean this up. We're gonna look, clear all drawings. Okay, we're gonna look at the momentum equations, and I'm gonna write this, I'm gonna use the tensor form of this equation. It's just a little easier, okay? All right, so d rho ui by, I have density around here. Let's pull out the density first, okay, because it's constant. So if you pull out the density and divide, so you take out the density from the time-dependent term and from the advection term, so you pull the density out, okay, and then divide by density, you get dui by dt plus du(j)ui by dxj, and then you divide on the right hand side. You get 1 over rho d tau ji by dxj. Remember, jj over here. We're differentiating with respect to j. Okay, and then minus 1 over rho dp by dxi plus gi. Okay, so note this I, these I, they correspond to this I, because that's the momentum component. Okay, all right. So, okay, that's a good step, but I think we can further clean up advection and diffusion. We can't do anything more on the transient term, nothing we can do to the pressure term nor the gravity term, but I think we have room in the advection and diffusion terms. So let's start with advection. Okay, so I'm going to take the advection term and I'm going to do the chain rule on the derivative. Okay, so duj(ui) by dxj is ui duj by dxj plus uj dui by dxj, right? Simply separating, doing the chain rule. Okay, now check this out. This is cool. What is duj by dxj? Oh, it's a repeated index. What did we say just a minute ago about mass conservation? dui by dxi is 0. duj by dxj is also 0 because it's a repeated summation. So this is coming from continuity. Remember, a repeated index is summed up. So ui duj by dxj is ui du by dx plus dv by dy plus dw by dz, which for constant density flows, incompressible flows, is 0. All right? So we took out one term in the advection term, and we're left with uj dui by dxj. This is still a repeated summation, uj and dxj. You're going to repeat the sum, okay? But I, in this case, is coming from the momentum equation. Which component of momentum? So the advection term reduces to uj dui by dxj, okay? This is good. So I'm going to update my momentum equation now. So instead of this term, now I have this term, okay? I have this term. There's still a summation implied over here, okay? Now, next, I want to look at the diffusive flux, okay? Called the stress tensor. So this is d tau ji by dxj. Again, remember, I'm summing over j. And remember, tau ji was mu dui by dxj plus duj by dxi, etc., all of this. Now, because we are incompressible, div u is 0, correct? We know this just from the conservation of mass. So this term disappears. Okay, we don't have to worry about the Kronecker delta anymore. Good. All right, so let's expand this. This is d by dxj of tau ji, mu dui by dxj plus duj by dxi. Now, if the viscosity is also constant, we can take it out of the derivative. So over here, I took out viscosity out of this derivative over here. Okay, so it became here. And now I have mu d by dxj of dui by dxj plus duj by dxi. Let's distribute the derivative. So if you distribute the derivative, you're going to get second derivatives. You get mu second derivative of ui with respect xj. Now, what is xj? It's going to be a repeated summation. So you get d2ui by dx squared plus d2ui by dy squared plus d2ui by dz squared. Agreed? Now this term, check out this term. d2uj by dxj dxi. I only have repeated summation on this j, xj, right? But it's on the outside. So here's what I'm going to do. I'm going after the continuity equation. So this one simply stays as is. So it becomes, because j is a repeated index, so for each component of momentum is going to look like this. It's going to look like what? Like a diffusion term, like a second derivative. So for the I component of momentum, it's going to be d2ui by dx squared plus d2ui by dy squared plus d2ui by dz squared. What is that? That's a diffusion term. So you see the diffusion in the stress tensor. It's just simply a diffusion term. Okay, what about the second component? It's the second term in this. d2uj by dxi dxj, or dxj by dxi. So I swapped now the order, because derivatives are, this is a continuous velocity field. I can swap the order of derivatives. I can differentiate with x first and then y, or y and then x. It doesn't matter, okay? And so if I swap the order now, I can pull out this duj by dxj, right? So I can pull out the one derivative here, duj by dxj. And what is that? That's the continuity equation, and that's equal to 0. right? So you knock out that term entirely. And then what happens? Your entire diffusive flux term becomes simply this very simple term over here, okay? So let's clean up. So this becomes my diffusion of my stress tensor, net diffusive flux contribution. And this is per component. And finally, this becomes my incompressible momentum equation with constant viscosity written in index notation. What do? You fix I, okay? I equal 1, 2, 3. For I equal 1, you have du by dt plus u du by dx plus uv du by dy plus w du by dz. If you are smart about this, you go and redo this. You say, okay, I'm gonna take this and I'm gonna expand this guy. Go from here to here. Can I do it? Yes, you can. You're fixing I and you're just repeatedly summing over j. You need to do this. I'm not going to assign you a homework, because what are you gonna submit to me? You're gonna submit, you can copy and paste the equations and do a submission. Okay? So instead, you're gonna hold yourself accountable to doing this yourselves. Okay? To doing these derivations yourself. So that will be your non-homework assignment, is going from all of these equations, index, dyadic, and the expanded form, okay? And again, in your equation sheet, I will also give you these expanded forms. And it will say when constant density, constant viscosity, this is what the equations will look like, okay? And these, my young pupils, are the Navier-Stokes equations written either in index notation or in vector form. Now you look at the vector form, what is cool here, you see the Laplacian term, which is diffusion. You see here the second derivative, which is a diffusion term, okay? So this enforces the idea, the fact that the stress tensor contributes as a diffusion term in the in the Navier-Stokes equations, okay? I'm gonna clear all drawings. Whew, a lot of math. Unfortunately, you need it, okay? You're grad students, you need to have seen this at least. Are you going to work with these all of your life? Maybe not, I don't know. But as a chemical engineer, you need to at least have seen them. But if you're doing modeling or anything that has to do with fluids, which you cannot escape, okay? Every time you breathe, these equations are operating in your airways and your lungs, right? So if you think about it this way, it will freak you out, right? There's like all of these rates of change and derivatives and expansion. All of this is happening. We can describe it with symbols, okay? So let me pull up the equation sheet just to make sure we are consistent, because I'm done with this, with these derivations. Got you to the finish line. Okay, handouts, equation sheet, summary of governing equations. Okay, perfect. So I'm going to open this. So this will be printed and given to you, okay? This will be printed and given to you. There's a bunch of things, expressions for the del operator in Cartesian, cylindrical, spherical, expressions for gradient, divergence, cross product. So you'll have a lot of stuff. All the stress tensor components, okay? All of the stress tensor components that we talked about, okay? And then the components in radial coordinates and then spherical coordinates, which, you know, you don't have to worry about. When we get to solving problems, we might use one of them. And then you see the momentum equations here in terms of stress, okay? So that's very important. It's very important. These are the Cauchy equations, okay? It's very important that you know when you need to use those equations, right? So those equations are used when the stress tensor or the diffusion tensor is not Newtonian. If I give you another formula, you take that formula and plug it into these equations, okay? Another formula for stress, that is. Same thing. Then next, again, in terms of stress for under all circumstances. And then in terms of velocities, so this is the Navier-Stokes. Here, notice, in terms of velocities, for a Newtonian fluid with constant rho and mu, okay? So you will see this, let me see, this is here in Cartesian, where's the Cartesian form? Yes, here, this is it. In terms of velocities, so this is the Cartesian form of the equations in terms of stresses, and in terms of velocities for constant rho and constant mu. I'm giving you all of these equations. You don't have to put them on your cheat sheet, okay? But you should know how to use them, when to use what. Now, in the problems that we will be solving together, we will be using the Cartesian form and the cylindrical form. Okay, we're not going to do a spherical form, but it is here, the spherical form. So these are the cylindrical form, and there's the spherical form here. So I would use the spherical form if we're doing flow over a sphere, for example, okay, analytically. All right. So as we move ahead, I will be spitting out these equations. We're going to take constant density, incompressible, constant properties, flows, and I'm just going to spit out these equations, and we're going to work with these equations. They're coming from here, and they were derived in class together. Your job is to make sure you can understand these derivations. You have until what, December 11, okay, to go through these, the dyadic form, the tensor notation form. I cannot stress that enough. You need to do these exercises. There will not be a homework assignment, but you will need to be able to go from one form to another, okay? If you don't, you might lose a few points on the final. I don't know how many, but there are questions about that, okay? There are questions about that. And on the final, I'll give you this equation sheet. You'll use it. You need to use it for, like I said in the beginning of the lecture, for the 3 problems you're getting. You're going to have to write down the equations, simplify the terms, etc., and submit your work either by hand. For those who are remote, you'll upload it. Okay? Thank you, guys. Good luck. Okay, I'll see you on Thursday.